further. Here is the single slit experiment. You are able to see once the light or waves pass through a slit, it's an obstacle. Automatically you are able to see the diffraction patterns. So this is called as Young's experiment. In the discussion of Young's experiment, we stated that a single narrow slit acts as a new source from which light spreads out. Even before Young, earlier experimenters including Newton had noticed that light spreads out from narrow holes and slits. It seems to turn around corners and enter regions where we could expect a shadow. These effects are known as diffraction. Can only be properly understood using wave ideas. After all, you are hardly surprised to hear sound waves from someone talking around a corner. When the double slit in Young's experiment is replaced by a single narrow slit, illuminated by a monochromatic source, a broad pattern with a central bright region is seen. You are able to see it here, with dark and bright fringes. So this is how the navigation is happening. Let's discuss more on the geometry of path differences for diffraction by a single slit. On both sides, there are alternative dark and bright fringe regions, the intensity becoming weaker away from the center. To understand this, we have shown a parallel beam of light falling normally on a single slit Ln. The diffracted light goes on to meet a screen. The midpoint of the slit is M. A straight line through M perpendicular to the slit planes meet the screen at C. We want the intensity at any point P on the screen. So as before, the straight lines joining the P to the different points of L, M, N can be treated as parallel, making an angle theta with the normal MC. The basic idea is to divide the slit into much smaller parts and add their contributions at P with a proper phase difference. We are treating different parts of the wavefront of the slit as secondary sources. Because the incoming wavefront is parallel to the plane of the slit, these sources are in phase. The path difference NP, so N, P and LP is equal to N, Q. So which is nothing but A sin theta, because L, P, N, P. So the difference is this area. This is the area, its difference, that's NQ, which is equal to A sin theta. Since the angle is really small, we'll make it as A theta. Similarly, if 2 points M1 and M2 in the slit plane are separated by a distance Y, this is the 1. The path difference is M2P, M1P is equal to Y theta. We now have to sum up equal coherent contributions from a large number of sources, each with a different phase. This calculation was made by Fresnel using integral calculus, so we omit it here. At the central point C, on the screen the angle theta is 0. All path difference are 0, hence all the parts of the slit contribute in phase. This gives the maximum intensity at C. This gives the maximum intensity at C, and the experimental evaluation observation is shown